Hi, welcome back. Today we're going to go through a couple of the problems on the application worksheet for 6.5. So I'm going to go ahead and show you the first two and then one on page 3, and then we can turn you loose at that point. So we've got Sydney here. She's on the Ferris wheel. It says it has a radius of 60 feet, suspended 10 feet above the ground. I'm going to stop right there. Um, so that tells us that the bottom, if you think of the Ferris wheel this way, when you're at the bottom of the wheel, you're at 10 feet. When you get to the midline here, you're at 70 because you got a radius, and then back up to 130, back to 70, down to 10 as you spin around this Ferris wheel. So we've got this 60-foot radius, um, top to middle, and then bottom to middle. So I know that my top point is 130, my midline is 70, that makes the low point 10. So I know I've got an amplitude here of 60. I've got a vertical shift of 70. So we'll get to that in a moment when we get to our equation. It says to write a function that describes her height above the ground and the number of seconds since she was a quarter of a way around the circle. So if you get on a Ferris wheel, you get on at the bottom. So it doesn't matter which way she's going. Either way, after a quarter turn, she is going to be at the midline. So we're going to start at 70 and then go up to 130, back down. If you had her start here and go back to 0, you could do that too, but we're going to go this way. So she's quarter way around. She's at 70 to 130, back to 70, back to 10, which is what you see this graph right here. Now we know it takes 2 revolutions every 6 minutes. That means 1 revolution every 3 minutes. If we got 1 revolution every 3 minutes, then we know it's 180 seconds per revolution. So Sydney's at 70 feet, up to 130, back to 70, down to 10, back to 70 in 180 seconds. So that's our labels. Again, you don't need the 45 and 135, but you need the 0, 90, and 180. And now at that point, we can find our K value here. We know that the period is 180 seconds. So if we set 180 equal to 2 pi over K, we have our period of pi over 90. And now I can get my equation. Our amplitude was 60. Our vertical shift was 70. Our K value here is pi over 90 times theta. Whether you make it T or X or theta doesn't really matter. There is no phase shift. We didn't move this graph left or right. So this is our equation right here. Part B, what is her height at 1.25 minutes? I change it to seconds, so that's at 75 seconds. So I plug 75 seconds into my equation. Please make sure that you are in radians when you do that. So at 75 seconds, she is at 100 feet. And the last part of this here says she's got her friend who wanted to get on after she was a quarter way around. How would her graph compare? Basically what you have, because her friend's getting on at the bottom of the Ferris wheel here, so you have a cosine graph, and she's getting on after she's a quarter way around. So she's going to start at the bottom, go up, and so forth. So we have a phase shift here because she is getting on later. So a quarter of the rotation, if we go back up here, it's 45 seconds would be a quarter rotation, right? So this is a half and then the second half. So every 45 seconds is a quarter rotation. So if we take our C over K, so C over pi over 90 equal to 45, we will get pi over 2. You didn't have to draw her graph, but I'm going to show you what that looks like. So I'm going to drag this up here so you can see what her friend's graph. That is not the one I wanted. Here we go. So bear with me here. So you can see her friend here is going to start after a quarter. So after Sydney's been on here for a quarter rotation, that's when her friend gets on. So that's this graph here. Her friend started at the bottom going to 70. So her friend would be here, Sydney would be there, and then her friend's at the top Sydney's at the bottom, and then they pass again, where they're side to side here at the same height. So that's what's going on. Again, you didn't have to draw her friend's graph, but just so you can see that starts at the bottom of the wave. That's why it's negative cosine down here. And so there's her equation with that 45-second delay, which ends up being pi over 2. Again, we did c over pi over 90 equal to 45. That's how you get the pi over 2. Again, at any point, if you need to go back or whatever, feel free to pause at any time when you need to write something down and take a look at these graphs here. So that was the first example, again, with Sydney's friend and Sydney on the Ferris wheel. So again, the original graph did not have a phase shift. Our second example, we've got Ben here. He is on the east coast of Canada, and he's observing the tide, so he can see that it's a high tide at 6:30 a.m., low tide at 12:30, and then high tide again at 6:30 p.m. So there's a 12-hour time lapse there from high tide, low tide, back to high tide. So we know that our period, you can see this here, period's 12 hours. The amplitude, our max height was 3.3. Our minimum height was 0.7. If we average that, we get 2 in the middle. So our amplitude is 1.3. 1.3 up, 1.3 down. So there's our amplitude. We've got a period of 12 hours. And so now we've got a start here. We've got 12 for A. We've got 1.3 for our H value for our vertical shift. If we scroll down here a little bit, they tell us that they want to write an equation with t equals 0 being midnight. I'm going to come back to that in 1 second. So they want 0 to be midnight, which means 6:30 a.m. is 6.5 hours. So instead of having this graph start here at 0, we've got to move it over 6.5 hours. And so first thing we'll do, we do our period. Our period's 12 hours, so 2 pi divided by 12 is pi over 6. Once we know that, then we can do our phase shift. Our phase shift is 6.5 hours. That's c over k. We know that k is pi over 6. When I cross multiply here, 6.5 times pi over 6, I get 6.5 pi over 6. If I double that to get rid of the decimal, I get 13 pi over 12. So that is my phase shift. I did move it to the right. You can see this cosine graph here. It says starting here, we moved it to the right. So minus 13 pi over 12. We've got the amplitude of 1.3. We've got that shift of 2 because 2 was the midline of the tide or of the water during the day. So again, this is the second one there with Ben and the tide on the east coast of Canada. Period was 12 hours. Amplitude was 1.3. Once we know the period's 12, we can do 2 pi divided by 12 to get our k value. Our phase shift, 6.5 is c over k. And we know k was pi over 6, so we can solve for c, and then we have our equation. Again, if you need to pause at any time, feel free to do that and stop for a second, especially on the graph if you need to label this. You don't have to put the time and the hours. You can just put 6.5, 12.5, 18.5 if you'd like. I just wanted to coordinate the time of day with that so you could see what was happening. All right, on mine, it's number 2. On yours, it's number 1. So the first example I did was the first page. This is the first one on the back of that first page. Now I'm going to do page 3, and I am going to go to the bottom there, which I believe it's number 4 on yours. It says number 5 on mine. Not that that matters. So we've got a child, a motion sensor attached to a child on a swing. So, the child's going up and down on this swing, measuring the height over time, and we want a cosine equation. So you can see here, we're not quite at the bottom at 0. I'm going to come back to that in a second. Here you see the bottom of the wave. So bottom, the top, the bottom. So since we're starting at the bottom, that's a negative cosine. And if you look at this carefully, you can see this, every one of these marks in the bottom is a second. So 1 second, 2 seconds, 3, 4, 5, so forth. So at the very bottom, we're at a half a second right there, and we're at the bottom again at 5.5, 10.5, and so forth. So basically what's going on is every 5 seconds is our period here. So we're at 0.25 at every 5 seconds. And so you can see at 1 second, and again at 5 seconds, so forth, we are at half a foot here. So this was off a little bit, but the period's 5 seconds. And so we know the midline here, we're kind of estimating this is 2, this next mark right there would be 2.5. So halfway is 2.25. This is 0, this would be a half, so right there is 0.25. So that means our midline is at 1.25. So I know my vertical shift. I know my amplitude then is 1, so that worked out really well. We can get our period here. We know it's 5 seconds, so 2 pi over 5. So there's my period there. And then I can do the phase shift. You can see the bottom of the wave here is a half a second over from 0. So I need to do my phase shift here of a half a second. So 1/2 second is C over K. And when I solve this for C, I'm going to get 2 pi over 10 or pi over 5. Again, I'm moving this wave to the right because you can see the bottom doesn't start at 0. It starts at half a second. So I have a pi over 5 phase shift. And now all these values will match up. So when I'm at 3 seconds, it'll say 2.25. When I get back to 8 seconds, I'll be back here. And we're seeing with the midline and the bottom values. So if you look at your table, it will match up there. So here is our equation that goes with this graph. The hard part is we were estimating. So, we got 2 right there, which isn't quite the top, 2.5 here. So right in the middle, 2.25 and 0.25 there at the bottom. So again, you can kind of see at 0 seconds, we're at a half. Again, at 5 seconds, we're at a half. And again, at 10 seconds, we're at a half. So that's how I figured out that the period was 5 seconds to get my K value. So you got those 3 down. That's half of what you need to do there. If you have any questions, feel free to check in during the day and we'll clarify. But the application worksheet will be due when you come back. And again, feel free to touch base if you need to during the day, and I will connect with you to answer any questions you have. Thanks a lot.